let me discuss another approach which is also very popular, and this is once again one of the most popular traditional approaches to solve this type of multi-objective optimization problem. Now, this approach is known as the goal programming. Now, here actually what we do is the decision maker will have to set the target for each of the objectives which he is going to maximize or minimize. Now, supposing that the targets are set, now the obtained objective function value will be compared with their respective target values and the deviation or the error that will be decided. Now, here this deviation or the difference between the calculated value of this particular objective and its corresponding target value. So, this particular difference it could be either positive or negative, and just to get the positive value we consider the mod. So, mod of f I x minus t I is nothing but is actually the deviation or the error in the mod value, that is the positive value, and this particular the deviation, the sum of all the deviations considering all the objectives. So, we try to minimize. Now, here once again the problem is the same. Supposing that say I want to say maximize or say minimize, let me put I want to optimize. It could be either maximize or minimize. So, optimize f I x, and x is nothing but a collection of all small x values. Say I have got m number of small x values or the design variables, and what I do is, and this particular I, that is the ith objective function, and I varies from 1 to up to capital N. So, I have got capital N number of objectives. Now, for each of the objectives, so we try to find out the difference between the calculated objective and the target value, and this particular difference we consider the mod, we sum them up and then we try to minimize. That means, we try to minimize the difference between the calculated objective and its target value. That means, your through the optimization, so we will try to hit the target value for each of these particular the objectives. So, that is the philosophy behind this type of the goal programming. Now, here I have written we try to minimize the absolute deviation of the objectives from their respective targets. Now, the problem is like how to set this particular the target. Now, if I take the same example like your the cost of a car and the accident rate of this particular car, and we have already discussed that if cost is more, the accident rate will be less and vice versa. Now, here actually what we do is how to set the target for the objective, that is the cost. So, what is the maximum amount beyond which I should not go? Similarly, what is the optimal accident rate which we should not exceed? Now, how to set this particular target, that could be the problem. Now, once these particular targets are set, it is now we can use this goal programming to find out or to solve this type of multi-objective optimization problem. Now, this is actually how to use the principle of goal programming to solve the multi-objective optimization problem. Now, then comes actually I am just going to discuss a third approach. This is actually popularly known as vector evaluated genetic algorithm. In short, this is known as Vega. Now, before I start, let me tell you that this particular approach is the first approach using genetic algorithm to solve the multi-objective optimization problem, and this particular approach was proposed by Schaeffer in the year 1985. So, as I told, this is the first approach. So, let us try to find out the principle, but this is not a very good approach, very efficient approach, but as this is the first approach using a genetic algorithm. So, let us spend some time on discussing the principle of this particular the approach. Now, here before I start, now let me tell you. Now, here what we do is we try to copy the first approach, that is the weighted sum approach, in an artificial way inside the genetic algorithm. How to do it? I am just going to discuss. Supposing that I have got a multi-objective optimization problem having say q number of objectives. So, q is actually the total number of objectives. Now, to solve this particular problem, what we do is we generate a large population size that is denoted by say capital N. Now, let us see how to proceed with this particular the approach. How does it work? Step 1, we create a population of size n at random. Now, step 2, carry out proportionate selection objective wise, thus create q subpopulation of size n by q each. Now, what does it mean? Supposing that I have got a multi-objective optimization problem having say 10 objectives. Now, what we do is, so we try to start with a large population size, say might be the population size n could be equal to say 1000. So, we start with a population of 1000 solutions selected at random, and next what we do is we carry out proportionate selection to get the mating pool, and while carrying out the proportionate selection we do it objective function wise. That means, out of the 10 objectives, first we concentrate on the first objective, try to find out one subpopulation, then we concentrate on the second objective, try to find out the second subpopulation, and this process I am just going to continue, and corresponding to the qth objective. So, I will be getting the qth subpopulation of solution. Now, let us see how does it works. Now, let me do one thing, whatever I discuss, let me just put it here in the schematic form sort of thing. Now, supposing that I have got a population, large population, that is capital N, and that is equals to 1000, and I have got the number of objectives q equals to 10. This is the initial population, this is nothing but the initial population. Now, this initial population I am just going to get one mating pool from this initial population. Now, for this mating pool actually what we do is, so we try to use the proportionate selection, and here the proportionate selection is done objective function y. Let me concentrate on the first objective first. Supposing that this is a binary coded thing. So, we have got the large number of solutions here. So, we concentrate on the first objective and try to carry out proportionate selection, and we will be getting the first subpopulation, and this subpopulation is very good in terms of the first objective function only, but it may not be so much good with respect to the other objectives. Next, I concentrate on the second objective function or the second objectives and try to form one subpopulation. So, this is good with respect to the second objectives, and this process will continue, and for the qth one, qth your objective function. So, I will be getting the qth subpopulation. Now, let me repeat. Now, this qth subpopulation is very good in terms of the qth objective function, but it may not be so much good with respect to the other objectives. So, this is the way actually we form the mating pool using proportionate selection, and once we have got this particular mating pool, now we go for the suppling. So, suppling is done just to put different weights on the different objectives artificially. Now, if you remember the first approach, that is the weighted sum approach, what we do is we put different weights on different objectives like W1, W2 and so on. Now, here the moment we do suppling, suppling means what? So, what we will do is we will change the position, the relative position of the solution, just like suppling of cards. So, the relative position of these particular solutions will be changed. The moment we do the suppling, as if we are putting some artificial weights on the different objectives, but we do not know the actual numerical values of these particular the objectives. So, this is the way actually we put different weights on the different objectives, and it is almost similar to the first approach, that is the weighted sum approach. And once you have got this particular the shuffled population, for example, say here I will be getting this particular the shuffled population. So, this particular shuffled population, now it is going to participate in crossover and mutation, and that completes actually one iteration or the one generation of this particular the GA. Now, this process will go on, and through a large number of iteration, there is a possibility that we will be getting one population of solution, which is very good with respect to this particular the objective function. But as we discussed, the concept of Pareto optimal front of solution we may not get here. We may not be able to draw the Pareto optimal front of solution corresponding to this particular the multi objective optimization problem. So, this is actually the drawback of this particular approach, but as I told that this is the first approach in which a genetic algorithm has been used to tackle the multi objective optimization problem. So, I thought I should discuss the principle of this particular the first approach using GA. But as I told, it has got some drawback in the sense it will not be able to find out what should be the Pareto optimal front of solution. So, this particular approach is actually very simple. Now, I am just going to start with some more efficient approaches to tackle the multi objective optimization problem using the concept of say genetic algorithm. Now, before I go for that, so I will have to define a particular term that is called the non-dominated solution. Now, let us see how to define this particular the non-dominated solution. Now, let us consider an optimization problem having say two objectives. Now, here actually what we do is let me just draw, say I am just going to consider a two objective optimization problem. So, F1 and F2, and our aim is to minimize say both F1 and F2. Now, let me consider any two solutions selected at random. Let me consider I have got a solution here say 1, I have got another solution here say 2. Now, if I compare between these two solutions in terms of the objective function, now here as I told our aim is to minimize both F1 and F2. Now, corresponding to the first solution, so this is nothing but F2 and this is nothing but F1. So, this is F1 and this is your F2. Similarly, corresponding to this particular solution, so this is my F1 and this is my F2. this is my F2. Now, if I compare these two solutions, solution 1 and solution 2 in terms of F1 and F2. So, corresponding to this F1 is more, F2 is more, and corresponding to this particular solution 1, F1 is less, F2 is less, and these are minimization problem. So, this solution 1 is a better solution compared to solution 2 in terms of both F1 and F2. That means, we can declare that solution 1 is a non-dominated solution, is a non-dominated solution, compared to solution 2. So, solution 1 is a better solution compared to solution 2, and this 1 is nothing but non-dominated solution which cannot be dominated. So, this is a better solution, and solution 2 is nothing but the dominated solution, and which is actually a what solution. This is actually the definition of the non-dominated solution. So, this particular term we are going to use very frequently while describing the principle of some other tools using GA to solve the multi-objective optimization problem. The same thing I have just shown it here. So, if I compare say this is once again the same problem F1 and F2 I will have to minimize. So, if I compare 1 and 2, definitely 1 will be a better solution compared to 2. So, 1 is nothing but a non-dominated solution. Now, similarly, if I compare this particular solution with that particular solution, definitely this will be a better solution or the non-dominated solution. And if I compare between this and this will be the non-dominated, between this and this will be the non-dominated, between this and this will be the non-dominated. So, these particular non-dominated solutions are nothing but the rank 1 solutions. We assign rank 1 to the non-dominated solution. Similarly, we have got the rank 2 solution, rank 3 solution, something like this, and of course, the rank 1 solutions will be better compared to the rank 2 solutions, and rank 2 solutions will be better compared to the rank 3 solution. And if I compare the average fitness, so the average fitness of the rank 1 solutions will be better compared to that of the rank 2 solution. Similarly, the average fitness of the rank 2 solutions will be better compared to that of the rank 3 solution. Now, my question is how to assign the ranks and how to make a computer program to assign these particular the ranks. Now, if I see the literature, there exists a few methods like how to assign this particular the rank. Now, here I am just going to discuss say one method like how to assign this particular the rank and how to get this rank 1 solution and the rank 2 solution. Now, once again the problem is as follows. Say in an initial population, say I have got a large number of solutions selected at random. Now, I will have to find out the rank 1 solution, rank 2 solution, rank 3 solution and so on. Now, for the time being, let me assume that I want to get only rank 1 and rank 2 solution. Let us see how to do it. Now, supposing that I have got a large number of solutions, say denoted by capital N, and n equals to 1000 here. Now, what I do is, so I will have to divide into two ranks, rank 1 and rank 2. So, here I have got one bin here or the bucket here. This is nothing but the non-dominated bin, and this is also known as the rank 1 bin, rank 1 bin. And here I have put another bin that is called the dominated bin, and that is nothing but the rank 2 bin. Now, this initial population I will have to distribute to the non-dominated bin and this dominated bin. Let us see how to do it in computer program. Now, what you will have to do is, so initially we select any point out of this 1000 at random, and what we do is we just put this particular solution, in the non-dominated bin. Now, supposing that, so this particular solution, that is the solution 1, that is put in the non-dominated bin. Now, what we do is, so this is directly selected here for this non-dominated bin and it is put there. Okay. Next, we go for the second solution. Now, once again this second solution, that is selected at random out of the remaining, like your 999 points. So, out of these 999 points, so any one is selected at the second point, and this second point is brought here to the non-dominated bin for the purpose of comparison. Now, if it is found to be better than the non-dominated points which are lying here already, it is put in this particular the non-dominated bin. So, the solution 2 is put here in the non-dominated bin. Then we go for the third point. Supposing that the third point is such, so this particular point is such that it is better than some of the points lying on the non-dominated bin, but it is found to be worse compared to some other points. So, if it is in between, so what we do is, so that particular third point we put it here, and the points which are found to be worse compared to, so this particular non-dominated solution, those are forced to the dominated bin. So, these particular the worst solution are actually forced to put in the dominated bin. Now, there could be another possibility that a particular solution selected from the initial bin, it could be worse compared to all the existing non-dominated solution here, and if that is the case, then that particular solution will be put in the dominated bin, and this particular process will have to repeat till we just consider all 1000 points. Now, these particular 1000 points will be divided into or distributed into two bins, that is the rank 1 bin. So, this is nothing but the rank 1 bin and this is the rank 2 bin. So, this will be distributed into rank 1 and rank 2. Now, if I want to get rank 3 bin, what you will have to do is, the rank 2 solution you put it here and repeat the process, and if you put the rank 2 solutions here. So, these rank 2 solutions here, and if you repeat this particular process. So, I will be getting the modified rank 2 here and the rank 3 here. So, the rank 2 solutions will be modified. Let me take a numerical example. Supposing that I have got 1000 points here, and say on the rank 1 basin I have got 200. So, the remaining 800 should come here. Now, I start this particular process with 800 here. So, here there will be 800 points, and we will be going to find out the modified rank 2 and the rank 3. Supposing that in the modified rank 2 I have got 300. So, out of 800, 300 I have put in the modified rank 2. So, the remaining 500 will go to the rank 3. So, this is the way the whole population will be divided into rank 1, rank 2 and rank 3 fronts. And once you have got this rank 1, rank 2 and rank 3 front, now actually we can take the help of the genetic algorithm to find out that particular the Pareto optimal front top solution. Now, the way the GA will help is as follows, like if I have got this rank 1, rank 2 and rank 3 solution. So, what we do is as we have already mentioned that the average fitness of the rank 1 will be better compared to the average fitness of rank 2, and average fitness of rank 2 will be better compared to the average fitness of rank 3. Now, actually the reproduction operator will try to select more number of rank 1 solution because their average fitness is better. So, there is a possibility that in the mating pool I will have got more number of rank 1 solution, and if you have got more number of rank 1 solution, then it will participate in crossover and mutation. There will be diversification of the solution, and there is a possibility that I will be getting better and better solution. So, there is a possibility that if I get rank 1 solution in first iteration, it is if it is like this, there is a possibility in second iteration I will be getting a Pareto front like this, third iteration I will be getting a Pareto front like this, and as iteration proceeds might be after a few iteration I will be getting this type of Pareto front, and GA will try to hit this type of Pareto front through a large number of iteration. So, this is the way actually we will have to find out the Pareto optimal front top solution. Now, the closer this particular front to this particular the origin, the better will be that particular the front in terms of the quality, but we cannot hit this particular the origin, that is 0 0, that is a globally minimum, or both f 1 and f 2 will be 0, that cannot be reached, because there will be some functional constraint, there will be some variable bounds. So, we will not be able to hit, you will not be getting a car at 0 cost and 0 accident rate, that is very hypothetical, but we will be getting a Pareto optimal front top solution which is very close from this particular the origin, and that will be the ideal the Pareto optimal front top solutions. Thank you.